Hi, and welcome to the fourth section of this course, Logistic Regression. In this section, we will rely on a generalization of the linear model solving a regression, but with the final objective of solving classification problems where we have to apply tags or assign all the elements from an observation set to predefined groups. In the previous section, we have seen an approach to model a part of reality as a linear function, which has independent variables, and bias, minimized an error function. The section will demonstrate the following topics: Logistic Function Predecessor, the Logit Functions, the Logistic Function, Univariate Logistic Regression, Univariate Logistic Regression with Keras. Now, we will see the first video of Section 4, Logistic Function Predecessor, the Logit Functions. Before we study the logistic function, we will review the original function on which it is based and which gives it some of its more general properties. Problem description. The kind of problem that linear regression aims to solve is not the prediction of a value based on a continuous function. This time, we want to know the probability for a sample of pertaining to a determined class. In this figure, we can see how the old and new problems can be classified. The first one, linear regression, can be imagined as a continuum of increasingly growing values. The other is a domain where the output can have just two different values based on the variable value. In the particular case of the second graphic, we can see a particular bias to one of the options, toward the extremes. On the left, there is a bias towards the 0 y value, and to the right, the bias is towards a value of 1. This terminology can be a bit tricky, given that even when we are doing a regression, thus looking for a continuous value, in reality, the final objective is building a prediction for a classification problem with discrete variables. The key here is to understand that we will obtain probabilities of an item pertaining to a class and not a totally discrete value. Essentially, when we talk about the Logit function, we are looking with the function of a random variable p, more specifically, one corresponding with a Bernoulli distribution. Bernoulli distribution. Before explaining theoretical details, it is worthwhile noting that a Bernoulli distribution is a random variable that takes a value of 0 with a failure probability of q equals 1 minus p, takes a value of 1 with a success probability of p. It can be expressed as a random variable x with Bernoulli distribution. This is the kind of probability distribution that will represent the probability of occurrence of the events as binary options, just as we want to represent our variable's existence of features, event occurrence, causality of phenomena, and so on. Link function. As we are trying to build a generalized linear model, we want to start from a linear function and from the dependent variable obtain a mapping to a probability distribution. Since the options are of a binary nature, the normally chosen distribution is the recently mentioned Bernoulli distribution, and the link function, leaning toward the logistic function, is the Logit function. Logit function. One of the possible variables that we could utilize is the natural logarithm of the odds that p equals 1. This function is called the Logit function. We can also call the Logit function a log-odd function because we are calculating the log of the odds for a given probability p. So as we can visually infer, replacing x with the combination of the independent variables, no matter the value of them, replacing x with any occurrence from minus infinity to infinity, we are scaling the response to be within 0 and 1. The importance of the Logit Inverse. Suppose that we calculate the inverse of the Logit function. This will let us write the function which is shown here. This function is a sigmoid function. Nice! We have successfully learned about Logistic Function Predecessor, the Logit Functions.